Okay, let's see, who do we have today? Faith is here. Let's see who else we have. Robert isn't here right now. Andy's not here, Ricky's not here. Madison. Rebecca. Lauren. Did I miss anybody? I don't think I did. Alright. Oh. And Samantha. Okay. I hate to start out this way, but I have some bad news that I need to inform us of, and that is that I cannot accept the quiz. And it's my fault that we can't do that. I sent the wrong version of the quiz out to everybody. It was the version that had the answers at the end. So, while I'm sure a lot of us didn't notice that, and so didn't use those answers, I still just can't in good faith accept it. So Friday of this week we'll be taking another quiz. It's going to be very similar to that one with some other stuff. Yeah. So it's not going to be the exact same quiz, but it's going to be very similar. Okay. And again, I apologize for that. That was a huge oversight on my part. All right. So lately I've been talking about some measures of location. Okay, so we were talking about mean, median, and mode last week, as well as a weighted mean. So these help us understand the best fit for our data. What is most representative of our data? Now, something else that's very useful when we're trying to do this is called standard deviation. Okay? So standard deviation, if we think back to our bell curves, our standard or normal distributions, why is it so washed out? Doesn't want to focus. But again, if we think back to our curves, gosh, it just doesn't want to show up. Let me try restarting this thing. Okay, that's better. So if we think about our normal curve, our normal distribution, we said that the median, mean, and mode all fall here when we have a nice even curve like this. Something that the standard deviation allows us to do is to say that things that are one quote-unquote standard deviation away from this line, this mean line, are what we can expect most of our data to look like. So on each side of this line here, I've got one standard deviation of distance. This is statistical distance, okay? So our standard deviation might be something like 5. Remember that this is a bunch of numbers down here, so we need a distance of 5. So maybe like we have, I don't know, 1 is here and 20 is here. Okay, so somewhere around here, if we count up 5 places on our number line, we have 1 standard deviation. Same thing on this side of the mean. If we count out 5 places on this side, we have 1 standard deviation. And most of our data is going to fall right there. In other words, that's what we can understand as being our normal data. This is what most of our data looks like. If we were to take the heights of people in all of the classes that I teach at Sul Ross, most people would be here. Of course, there are some people who would fall outside of this, like on this side, which are a little bit shorter, and some people who are a little bit taller. But they are the people who we would call outliers because they're, way outside of our most data, our bulk of our data. Okay? So knowing the standard deviation can help us understand what our real average person looks like, or real average price looks like in a store, real average, whatever data we're looking at. Okay? Now, before we actually get into the formula and how to do it, we need to cover some symbols. First of all, remember that we have samples and populations. So standard deviation is actually calculated slightly different between a population and a sample. For the most part, they're the same calculation with just one tiny little difference. So their symbol has a difference as well. When we're talking about the population standard deviation, we use a symbol called sigma. Greek letter sigma, and it's the lowercase sigma. So it's like an O with a tail on top of it. When we're talking about a sample standard deviation, we use S. Okay. Now, standard deviations, whether it be a population or a sample, also use a different definition of mean. They both use mean in their calculation, but they use a different version of it. So the symbol that we use for the mean of a population is Greek letter mu. And the sample mean is called x bar. It's an x with a bar on top of it. Okay, and there's one more thing. We already know this one. The number of data points we have in a particular set of data is n. Okay? So we now have all the pieces and parts that we need to construct our formula. Any questions so far? Okay. Now again, the reason we have these symbols is to differentiate what we're talking about. Are we talking about the standard deviation of a population, or is it the standard deviation of a sample? Is it the mean of a population? Is it the mean of a sample? That's why we have these different symbols, again, so that we know what we are trying to describe. So, a standard deviation is kind of like taking a mean twice. So let's start with population standard deviation. So again, this will be sigma equals the square root of the sum of all points, so x minus mu, so all points minus the mean squared over n. So remember that mean, whether it be for a sample or for a population, mean is going to be add up all your numbers, all your data points, and then divide by the number of data points you have. This is actually essentially doing the same thing. So we get the mean first, right? So we get this mean, but then we use that mean again. Each of the points in our data set will be subtracted the mean, so minus the mean, but we add up all those points and then divide by the number of points we have. So it's again like taking the mean twice. Okay? So let's try that. So let's say we have heights of pet dogs, and we've got 5 of these dogs. And we measure their height from the bottom of their paw to the top of their shoulder in millimeters. Okay? So our data is, let's see, 600 millimeters. 470, 170, 430, and 300. Okay. So if we want to find the standard deviation of this data to see, where most dogs fall, then we are first going to need the mean. So let's go ahead and get that mean. Well, normally we'd order these from least to greatest, but for mean we don't really need to do that. We just need to add them all together. So let's see what we get. So 600 plus 170 plus 470 plus 430 plus 300. So we get a sum of, so the sum is 1,970, and then we need to divide by the number of data points we have. So that's 5 data points. So if we divide this by 5, our mean, our population mean, is 394. Okay. So, again, that's the first time that we find a mean. What we need to do now is take each of these data points. Basically, these are our x's. So each of these data points, we're going to subtract our mean, like we're doing here. And then once we have all of those, we'll add them up and get the average of them, the mean of those values. So first of all, 600 minus our mean, 394. So 600 minus 394 is 206. 470 minus 394 is 76. 170 minus 394, is negative 224. Okay. Then 430 minus 394 is 36. And then 300 minus 394 is, of course, negative 94. Now, before we add all these up, we got this little guy here, square. So we're going to need to square all of these, then add them up and get our mean. So luckily I have this already done. If we square each of these come out to be 42,436. 5,776. Oops. I'll just rewrite this. 42,436. 5,776. 50,176. 1,206. 296 and 8,836. Okay? So now we need to find the mean of these. So we found our mean of our original, subtracted the mean from each of these data points, and squared it. So once we square, we need to find the mean of all these numbers. Okay, so if we add all these numbers up, we get 108,520. And we need to divide that by the number of data points we have, which is 1, 2, 3, 4, 5. So to divide that by 5, let's see, we get 21,704. So we got our mean, we subtracted our x minus our mean and squared it. We found our mean of that new data, and now the last thing we have is this square root. So we need to take the square root of this number. So let's see, 21,704, take the square root of that. And since we're talking about the height of dogs in millimeters, let's just round to the nearest millimeter. So our standard deviation for this set of dogs is 147 millimeters. Okay, so again, what does this mean? This means that if we were to look at these dogs' heights as a normal distribution, the mean is right about here. The mean, again, being at 394 millimeters. So the just straight average dog in this population is 394 millimeters tall from paw to shoulder. However, that's just a single number. That's a straight line cut right down the middle. Not every dog is going to look exactly like our mean. So our standard deviation says, well, if we go one standard deviation from our mean, so 147 millimeters in this direction and 147 millimeters in this direction, this should contain most of our data. In fact, in this particular example, it contains 68% of our data. And we'll figure out how to find those percents later. So 68% of dogs in this population are going to fall within one standard deviation of our mean. So this is a better way of showing overall what these data points look like, what these dogs' heights look like. And of course, and like the example I have here says, you know, a dachshund's really, really short. But that's just dachshunds. Most dogs are not going to be that short. They're going to be somewhere in here. A Great Dane or an Irish Wolfhound is going to be really, really tall. But again, most dogs aren't going to be in that range. Most dogs are going to be about the same height. And they're going to be in this area here where we are one standard deviation on each side of our mean. Does this make sense? Okay, so again, that's what standard deviation is useful for. It's for showing where most of our data falls. It's a good description of what our data looks like overall as a range of an average instead of just a straight line average. Okay, but I also said that we have sample standard deviations. So remember that a sample standard deviation is denoted by S. And like I said, it's almost the exact same. We've got sigma, or capital sigma for our sum of x numbers minus x bar. Remember that x bar is a sample mean, not a population mean, a sample mean, squared, all over n minus 1. That's the one difference in this. So again, the only difference between sample and population is that in a sample, instead of dividing everything by n, we divide it by n minus 1. Okay. See if I can find a good example for us here. Population sample. Okay. So the example that I have here says a sample of 4 students was taken to see how many pencils they were carrying. So again, this is a sample. It's not everybody in the classroom. It's not everybody in the school. It's not everybody in whatever. It's just a sample of students, and it's a sample of 4 students. So because it's a sample, we need to use our sample standard deviation. So we have responses here: 2 pencils, 2 pencils, 5 pencils, and 7 pencils. Okay. So just like before, we still need to find our mean. We'll need to find x bar. And even though it has a different symbol, it does still have the same calculation. Again, this is just to show that we're talking about a sample instead of a population. So 2 plus 2 plus 5 plus 7 will give us 16. And then we need to divide that by the number of data points we have to get that mean. So divide by 4. And we get 4 for our x bar. So again, our sample mean is 4 in this case. And now we need to subtract that from each of our data points and then square them. So 2 minus 4 is going to give us what? -2. Same thing for that one. It's also going to be -2. All right, 5 minus 4? +1. Yeah. And 7 minus 4? 3. Yeah. And then we need to square each of these. So what's negative 2 times negative 2? Well, 2 times 2 is what? Anybody? 2 times 2 is 4. Negative times negative is a positive. So negative 2 times negative 2 is positive 4. What's 1 squared? 1 times 1. 1, thank you. And 3 squared. 3 times 3. 9. There we go. Okay, so we've got our new data. We've taken each of these points, subtracted the mean to get these, and then squared them, and we've got our new data points. Now we need to take the mean of these, but remember, we're going to not use just n, but n minus 1. So first, let's add these up. So 4 plus 4 plus 1 plus 9. So 4 plus 4 is 8, plus 1 is 9, 9 plus 9 is 18. And then we need to divide by n minus 1. So what is my current n? 4. And then n minus 1 is 3. So when I divide 18 by 3, what do I get? 6. So we have a standard deviation of 6. I'm sorry, not a standard deviation of 6. There's still one more thing we have to do. What do we need to do? Square root it, yeah. Sorry about that. So take the square root of 6, and what do we get? We get 2.45. Okay. So again, what this means is if we think about this as a normal distribution, and our mean, 4, is right here, then we count 2.45 spaces out. So this is 4. We count this way 2.45 spaces. Let's see what that actually is. 4 minus 2.45. And so, again, this is one standard deviation on this side. This is another standard deviation on this side. So what we can see is that most of these students, if we were to expand this sample to thinking about a population, we could expect that most students would fall somewhere between 1.5 pencils, so basically 2 pencils, to 6.45, so 7. And that's actually what we happen to see with our sample. Okay? Any questions? Okay, so once again, population and sample standard deviation are very similar, almost exactly the same. The one place that they are different is that in normal standard deviation, or what I should call population standard deviation, we just divide by n when we get to the end here. In sample standard deviation, we're going to do n minus 1. Okay? So once again, any questions? No questions? Okay. So one more time. Symbols. These symbols are going to be on the quiz. I'm going to ask you what they mean. Okay? So if we have a population standard deviation, it's sigma, this O with like a tail on top. Sample standard deviation is just S. Population mean is Greek letter mu. That's spelled MU. I guess I'll spell sigma too. Okay? Sample mean is X bar. So we've got a different symbol for the types of standard deviation. We've got a different symbol for the types of mean. And then again, number of data points as always is N. Okay. So I think that will probably do it for today. Remember, quiz on Friday. Again, I'm really sorry about what happened with the quiz last week. I appreciate the work that y'all did on that quiz, and I will probably end up using it as a extra credit grade or something, but I can't count it as a normal quiz grade. Okay? So I'll see y'all on Wednesday, and I hope y'all have a good day.